We've spent time on this channel asking why nobody's visited us and what the great filter might actually be. Here's a theory that ties both of those together, and it's not life is rare. It's that a planet capable of keeping complex life alive for billions of years without ever fully resetting might be the rare part, and once you see the actual list of things Earth had to get right simultaneously, it's genuinely hard to argue otherwise. Start with the obvious one, the habitable zone. It's necessary, and it's nowhere near sufficient on its own. Earth sits at the right distance from the Sun for water to exist as a liquid rather than freezing solid or boiling away, the so-called Goldilocks zone. That's the factor everyone already knows. It's also just the entry ticket. Mars sits inside a version of the habitable zone too. So technically, does Venus. Neither one has anything close to a thriving biosphere. Distance from a star gets you in the room. It doesn't get you anywhere else on this list. Next, the Moon, and this one's more interesting than it causes tides. Earth's moon is unusually large relative to its planet. No other rocky world in the solar system has a moon anywhere close to this proportional size. Its gravity helps hold Earth's axial tilt steady at roughly 22 to 24 degrees, which is why our seasons are predictable rather than chaotic. Early modelling in the 1990s suggested that without a large moon, a planet's tilt could swing wildly and unpredictably over time, repeatedly scrambling climate before life had a chance to settle in. Worth being honest, though, more recent simulations from 2012 walk that back somewhat. A moonless Earth would likely wobble more, somewhere between 10 and 50 degrees over long timescales, but probably not chaotically enough to make complex life outright impossible. The argument's been weakened, it hasn't been eliminated, and the moon may have saved Earth from an even more fundamental problem, getting stuck facing its star permanently. Most planets sitting close enough to their star to fall inside the habitable zone end up tidally locked, spinning at exactly the same rate they orbit, so one side permanently faces the star in blazing daylight, while the other stays in permanent freezing night. That's close to the default outcome for planets orbiting small, cool red dwarf stars, which is a real problem, since most stars in the galaxy are exactly that type. Earth escaped this fate mainly because the Sun is large and far enough away that its tidal pull on us is comparatively weak, but calculations suggest it wasn't guaranteed. If Earth had formed spinning more slowly than it did, with no large moon adding its own stabilising drag, models suggest it could plausibly have tidally locked to the Sun over the following few billion years, the same fate that's already overtaken most of Mercury's rotation, and the likely default for planets like Proxima b. Earth's 24-hour day isn't just convenient, it's evidence something worked out. One more orbital detail worth including, easy to overlook next to the more dramatic factors. Earth's orbit is almost perfectly circular. Earth's orbital eccentricity, a measure of how stretched an ellipse an orbit traces, sits at just 0.0167, close to a true circle. That matters because a more elongated, eccentric orbit would carry a planet meaningfully closer to and farther from its star across a single year, layering large temperature swings on top of whatever seasonal changes axial tilt already produces. Earth's near-circular path means our distance from the Sun barely changes year-round, leaving axial tilt as the main driver of seasons, rather than one variable fighting against another. Then there's plate tectonics, which might be the single most defensible item on this entire list. Earth is, as far as we can tell, the only body in the solar system with active plate tectonics. And it's not just interest in geology, it's a planetary thermostat. Volcanoes release carbon dioxide, rain and weathering pull it back out of the atmosphere into rock. Subduction drags that rock back underground, and volcanism eventually releases it again. That cycle, running continuously over millions of years, is what stops a planet sliding into a permanent ice age or a runaway greenhouse. You don't have to imagine what the alternative looks like. Just look at our neighbours, Venus, stuck in a runaway greenhouse at 465 degrees Celsius, and Mars, frozen and thin-aired, neither one with anything resembling this regulating cycle. The magnetic field solves a completely different problem. It's the reason Earth still has an atmosphere at all. A molten, churning core generates a global magnetic field that deflects the constant stream of charged particles blasting out from the Sun, the solar wind. Without that shield, the solar wind slowly strips a planet's atmosphere away into space, particle by particle, over geological time, Mars is the textbook example. It's widely believed to have lost most of its original atmosphere, this way after its core cooled and its own magnetic field faded. Earth's still spinning, still molten, still generating that shield billions of years later. Jupiter's role is the one you'll hear cited most confidently, and it's also the one that's been most seriously reconsidered recently. So it's worth being honest about that. The traditional version of the story, Jupiter's enormous gravity acts as a cosmic vacuum cleaner, pulling in or flinging away comets and asteroids that might otherwise threaten the inner solar system, effectively shielding Earth from a much higher rate of catastrophic impacts. It's a satisfying story, and it's still commonly repeated. But more recent orbital simulations have complicated it. Jupiter's gravity doesn't just remove objects from danger, it can also fling some of them into new, more dangerous paths depending on the specific dynamics involved, meaning its net effect on Earth's impact rate is genuinely more ambiguous than the shield story suggests. Real, useful, still being argued over science, not a settled fact, whatever the simplified version says. And there's a bigger picture location requirement too, one operating at the scale of the entire galaxy rather than the solar system. Where a star sits within the Milky Way matters. Too close to the galactic centre, and radiation levels and the sheer density of nearby stars make catastrophic events, supernova, gamma-ray bursts, a much more frequent hazard. Too far out, and there simply isn't enough heavy element material around to build rocky planets in the first place. Our solar system sits inside what's been termed the galactic habitable zone, not the safest possible spot, not the richest, somewhere in the workable middle. And then there's the star itself. The sun isn't just present, it's the right type, and that turns out to matter more than most people assume. The sun is a G-type star, stable, long-lived, and, crucially, not the kind of star most habitable zone planets we've actually found tend to orbit. Most stars in the galaxy are red dwarfs, smaller, dimmer, and cooler than the sun. That makes them far easier to detect planets around, which is exactly why so many of our discoveries cluster there, as of late 2025. Of roughly 70 known exoplanets sitting in the liquid water temperature zone, about 50 of them orbit red dwarfs, but dim stars force their habitable zones in close, and that closeness is the problem. Red dwarfs are known for frequent, violent flares and radiation bursts, especially early in their lives, capable of stripping a nearby planet's atmosphere away entirely. A planet can be at exactly the right temperature, and still be getting scoured by radiation its star can't stop producing. The sun, by comparison, is calmer, bigger, and further away from anything orbiting it at a habitable distance, genuinely one of the quieter, steadier stars a planet could hope to end up around. So genuinely, what makes Earth so perfect? Not one factor. A stack of them, arriving together. A stable, well-behaved star, calm enough that its planets aren't being scoured by the kind of radiation most red dwarf worlds have to contend with. A disproportionately large moon, holding our tilt, roughly steady, and likely saving us from tidal locking altogether. A near-circular orbit that keeps our distance from the sun steady year-round. The only confirmed active plate tectonics in the solar system, quietly regulating the climate for billions of years. A magnetic field that's kept our atmosphere from bleeding away into space the way Mars's did. A giant neighbour whose actual protective effect is more complicated than the popular version claims. And a spot in the galaxy that's neither too dangerous nor too empty. None of these factors is exotic on its own. Plenty of planets have a large moon. Plenty sit in a habitable zone. Plenty have active tectonics or a magnetic field. What's genuinely rare, at least in everything we've found and catalogued so far, is a single planet holding all of them at once, around the right kind of star, in the right kind of orbit, at the right point in the galaxy, for billions of consecutive years without any one factor failing and undoing the rest. Despite thousands of confirmed exoplanets now catalogued, we have not yet found another world that clears every item on this list simultaneously. That might simply mean we haven't looked hard enough yet, or long enough, or with good enough instruments, a real, live possibility worth taking seriously. But it might also mean the honest answer is that this specific combination is genuinely difficult to assemble, and Earth just happens to be the one place we know of where it all came together at once. This is one of the leading honest answers to the question we keep circling back to on this channel. Maybe the universe isn't short on planets, or even short on simple life. Maybe it's short on planets that got every one of these things right at the same time for long enough. If that's true, the silence out there isn't evidence nobody's home. It might just be evidence of how much had to go right for anyone to be home at all, including us. If you found this useful, hit subscribe for more of these, and a like genuinely helps the channel more than you'd think.